Okay, good evening, everyone. I think we'll start. The timer was a bit slow. Welcome to the Astronomical Society of Edinburgh. We have a few technical problems, so things may hang, but we'll get there. Welcome wherever you are. We've got a number of members and visitors in the hall here in Edinburgh. We have members on Zoom, and we have visitors on YouTube, so welcome wherever you are in the world. It's a special night for us tonight, not only because we've got Andy Lawrence, one of our honorary presidents, speaking to us, but also it's our AGM, but we'll also have an SGM before that starts. But that's later on in the evening, and we'll turn YouTube off before we have those parts of the meeting. I don't think, unless you remember, you'll be interested in what's happening there. But this is what's coming up tonight. We've got a few introductory slides from me. What talks are coming up over the next few months. And then we have the main event of the evening, which is Making Pictures of the Sky, 200 Years of Astronomical Imaging, and that's from Professor Andy Lawrence. Jim Nisbet's going to give us a quick rundown on the sky in June, which, as it's mostly twilight, will probably not be that long. And then after that, we'll move on to our special general meeting and annual general meeting. We have a couple of new members this month, Mike Newton and Alexandra Onea, so can we welcome them in the usual way? Lots of ways of staying in touch with us. All the things that we do are on our website, lots of information on there, so keep an eye on that. We have a Facebook page and a Twitter feed as well. We have lots and lots of amazing talks on our YouTube channel as well, and this one will be on there afterwards as well, so have a look at that. All the talks we've had over the last 3 years or so, 3 or 4 years. We have a Flickr group as well. Our members taking amazing images on, so have a look at that as well. The number of people in society taking images is growing rapidly, and they're increasingly amazing. So these are the talks we have coming up over the next couple of months. On the 7th of June, that's next Wednesday. For members only, we have our Imaging and Observing group. On the 16th of June, this is an online-only talk, A Traveller's Guide to the Stars by Les Johnson. That will be on Zoom for members and YouTube for visitors. The 7th of July, we'll have a hybrid meeting, so it'll be here and on Zoom for members and YouTube for visitors about JWST from Dr. Pamela Klassen. Our Imaging and Observing group again on the 12th of July, and the last talk before our August break on the 21st of July is an online-only talk, An Astronomer's Guide to the Chemical Elements from Dr. Mike Leggett. And then we will start back, not on the 1st of September, actually, as it says there, but on the 8th of September, because we can't get in here because of festival activities, so it'll be slightly later on. And that's the introductory stuff, so it's over to Professor Andy Lawrence. Yeah, do you want to put that in also?
You want this? Oh, there we go. And are we getting this on Zoom and YouTube okay? Fantastic. Right, we are cooking with gas. Right, well, hello everybody. It's very exciting to be here. Somehow I've been reminded this evening I managed to conspire to be here at the annual general meeting, swelling the numbers. Okay, so there's the full version of my title. Making Pictures of the Sky, 200 Years of Astronomical Imaging from the Royal Observatory Edinburgh. Now, first of all, why Edinburgh? A lot of the things I'm going to show you are really quite general, apply to astronomers all over the world, observatories everywhere. But a lot of these things have happened in Edinburgh, but also Edinburgh is a nice hook on which to hang this story, and I think it will appeal to all of you as well. So, Edinburgh. Now, why 200 years? Well, 1822, so 201 years ago, 1822 is when the observatory in Edinburgh became a royal observatory, when it was blessed by King George IV and his famous visit in 1822. It's the same reason why that street out there is called George IV Bridge, okay? So it's all to do with the same visit. Now, of course, since then, as you know, so there's the observatory in those days was, let's see if the pointer works. Oh. Hang on. No. Yeah, got the power switch. There we go. All right. So here's Carlton Hill. That's the City Observatory, and this is where the observatory originally was. And of course, in 1894, it moved up here to Blackford Hill, and that's where it still is today, and where I work. Okay, so my talk today is going to have 5 themes. Eye, hand, and telescope, the atmosphere and why we hate it so much, mapping the sky, making surveys, capturing light, how we done, as probably many of you know, was Charles Piazzi Smythe. Now, I think, as I understand it, it was Charles who decided to change the pronunciation to the more pretentious Smythe rather than Smith, I believe, okay? Historians are divided on this matter. But there he is, and he was the second Astronomer Royal for Scotland after the first, which was Thomas Henderson. Now, Charles Piazzi Smythe was a very talented and very busy astronomer, but he was also a quite talented and prolific artist in various ways. So this, for instance, is one of my favorite ever pictures. It's his sketch of the stars as seen from the top of the mountain in Tenerife during his famous trip of 1856, which we'll touch on a little bit more later, in which he proved that mountaintops is the right place to do astronomy. You can also see here, this is the island of La Palma, where many telescopes, where I visited many, many times. So that was 1856. This is the aurora as seen from Edinburgh, with the moon in shot there as well, in his sketch. From 1875, I think, and he drew the aurora many times. He was also very fond of observing and drawing the zodiacal light. How many people here have seen the zodiacal light? A handful, yeah. It's very, very hard to do. I hadn't seen it myself until 2016, okay, on a trip to Tenerife. And if I'll just drop names, I was shown the zodiacal light by Brian May, so there we go. But this is Piazzi Smythe's drawing of the zodiacal light from South Africa during his first job. I think this picture is from about 1844, 1845, something like that. Here, much later on, here is his picture of the zodiacal light as seen from a trip to Palermo. And don't quote me on this, but I think that was about 1876. Now, the thing is, so he drew these pictures, and they're quite accurate as well as being very attractive. But it wasn't just about pretty pictures though they are. He and others could make measurements and recordings and take notes, the time things happened and so on, which was scientifically important. So this is from the official report to the Admiralty after his trip to Tenerife in 1856. And this is the zodiacal light, and this is his key point. This is not. This is lunar twilight, okay, scattering from the atmosphere. So he was able to very carefully distinguish between them, but he was also able to measure the angle of the zodiacal light. And through that, he was able to test two rival theories of the time about how the zodiacal light came about. I think people did generally believe, as we do now, that it's light scattered by dust particles. But some people believe that that was dust surrounding the Earth, and others believe that it was dust surrounding the Sun. And he showed that the second of those is correct. It's dust surrounding the Sun. So there we go. And that's why Brian May was interested in all this. Because, as you know, he loves stereophotography. We'll come to that later. But he's also obsessed with the zodiacal light. That's what his PhD thesis was on. Okay, but things get a lot more powerful if you add the telescope to the hand and eye combination. So the telescope does two things for you. It makes things deeper and sharper. We'll come to this in a moment, but just to explain these pictures. This, I think, is from a magazine. It's probably from the Edinburgh Illustrated News, I think. And it's not quite clear, but we think this is a sketch of Piazzi Smythe observing in Elkies near Aberdeen, using the Great Trophy telescope that was originally in the Great Exhibition and got moved to Aberdeenshire. This is a student called Sophie, who you'll see more of later, observing from ground level in Tenerife. Okay, deeper and sharper. Let me show you deeper first of all. So this is from a very nice web page by David Morton, okay? And what he's showing us here is the difference as you go from naked eye to binoculars to a 3-inch telescope, and a 2-degree field of view centered on Epsilon Lyrae. And so with the naked eye, you can just see those two stars, that double star. With a pair of binoculars, you see about kind of half a dozen stars. With a 3-inch telescope, you can see a couple of dozen. Okay, and basically what's going on is that small apertures for small optical instruments than it is for big ones. Okay, so here, so the eye, the pupil of the eye can resolve about 1 minute of arc at 60 times better. And we'll come to it in a moment to why you can't do better and better and better, okay? But that's about the best you can do. But then, if you like, in terms of what you can separate those two cars 60 times further away, if you could see them. And I've put an illustration together here of what this means. So this is not something you could actually see with your naked eye. This is part of an infrared survey that myself and colleagues made some years back. This is in the center of the Milky Way with an infrared camera, but it doesn't really matter. Point is, it's center of the Milky Way, squillions of stars. That's a technical term, squillions. Right, squillions of stars, quite tightly packed, okay, with about 1 arcsecond resolution. What I did then was take this digital image and I just ran it through some smoothing software to produce this. So you can't see this with your eye because it's in the infrared and it's much too faint. But if you could, this is the resolution you get with the eye going from there to there. So you can see the point. Basically, then you lose an awful lot. You don't really know what's going on, what star is what. It's not just that the picture looks better here. You really don't understand what's happening here. That looks like one fat object, and in fact, it's a bunch of objects. Okay, so that's the sharpness. So that's the first part, eye, hand, and telescope. Now I want to talk about the atmosphere and why we hate it so much. So this business of getting bigger and bigger telescopes to get sharper and sharper images, there's a limit to that, which is our own atmosphere. And this is what every amateur astronomer as well as professional astronomer hates astronomical seeing. Okay? As the light comes down through the atmosphere, refraction in the atmosphere makes the light bend from one side to another. And as it arrives, that makes the image swim about. Now, I'll show you exactly what I'm up to, on about. Top left there, this is a 10-inch Me telescope up on Blackfoot Hill, just looking straight across the horizon towards some buildings in Edinburgh. And I think if I do this, that movie should run. Right, so can you see it? It's just kind of sort of swimming about, okay? And as I say, I think every amateur astronomer knows this effect. The lower picture, we'll take a look at this one. This is a kind of zoomed-in time-lapse on a much smaller scale of, oh no, which star is this? I think it's Epsilon Aurigae. And it really is hard to see what's going on. These are so-called speckles, and they swim about, merge together, separate out. It's absolutely horrible. And on the right there is Sophie trying to observe Jupiter from the ground, which mostly is fairly horrible. But one night, with the same telescope in Holyrood Park, it was much better one evening, and we got this image. This is what Sophie got with a little webcam on the 10-inch Meade. So there's Jupiter. Not bad. Now, you can do better. That's a kind of frame from a video, right? That gives you an impression of what you're seeing at any one time. You can get better if you stack the images, if you integrate. And that same night, this is what you got from integrating. Pretty good. But you can do even better. Now, this is sharpened. Now, how? There's a technique called lucky imaging, which, again, many amateurs use, where if you have a kind of video frame rate, every so often, there's a little sort of fraction of a second where the seeing is better than normal. So as you see the frames coming through, you grab the good ones and throw the others away. And then possibly also you realign them so they sit on top of each other. And if you do that, you can get a much better image. And so that's what we did there. Now, this is the interesting thing, the observatory at the Cape in South Africa. And so when he wasn't being an assistant astronomer, he also had a job for a while on a geodetic survey. He was sent out with others to kind of make measurements on the landscape to do surveying. And when he did that, and this is a sketch he made while on one of those trips in the Karoo Desert. When he did that, he found that the stars were much sharper than they were in town, and especially if he was on the top of a mountain. And then he became convinced that you need to get above as much atmosphere as you can, and then from the top of mountains was the right place to do astronomy. So he came to Edinburgh, and some years later, he got the chance to try and prove he was right. He raised money from the Admiralty to go to Tenerife, an exhibition, and together with his wife Jessica, who was a geologist, they lived on top of the mountain in Tenerife for 2 months and made astronomical measurements. So there's Tenerife today. It's Telescope City, because everybody knows it's a good place to observe. But he was the first person to do this. Here's my picture of this stone house that they built and lived in on the peak of Guajara in 2016. And it worked. Now, on the left here, this is a sketch he made of the double star Alpha Piscium, not quite sure. Anybody got an opinion? Well, okay, fine. So it's separated about 2 arc seconds. This is his observation from that telescope in Elkies. It's just a sort of snaking mess, okay? This is what he saw in Tenerife. Cleanly separated, and these rings are real. They're so-called airy rings, because it was with quite a small telescope, so you could see the diffraction rings from the small telescope. So it was amazing. Oh yeah, that's a little time-lapse movie. It's not the same star, but you get the idea. This is what speckles do to you, the atmosphere. Even better, I think, on the second observing station he used, Alta Vista in Tenerife, he made this sketch of Jupiter. The conditions he had were so good, he got these incredible sketches. And when you compare this to kind of modern spacecraft pictures, he pretty much got it correct. So this picture at the time was absolutely astonishing. Good old Piazzi Smythe. And so anyway, so gradually word got through, and this, cutting a long story short here, people were convinced, and now, of course, ground-based observatories normally are on top of mountains. Here's one of my favorites. This is the William Herschel Telescope on the island of La Palma. And here's me in the control room observing on the William Herschel Telescope. But of course, that's all very well, but to really beat the atmosphere, what you've got to do is just get rid of it, get away from it completely, get into space, get above it. Now, of course, this is not trivial because it's very expensive and difficult to do this, but it is the way. And that's the Hubble Space Telescope floating serenely above the Earth. Now, just to show you what it can do for you. Oh, I should emphasize that the ROE has been into the sort of space game for quite a long time. Not necessarily always in the optical, but for instance, here is Colin Humphreys standing next to the nose cone of a Skylark rocket that had a UV experiment put into it. This much more, and we'll come back to this in a little bit. This is Alistair Glass building the mid-infrared instrument for JWST, which is flying now in the lab in Edinburgh. And we'll come back to some of that a bit later. But here's an illustration of what getting up to space can do for you. Because suddenly you can get past that 1 arc second kind of limit that you get from even about best ground-based observatories because of the damned atmosphere. So with the Hubble Space Telescope, you get 1/10 of an arc second, right, 10 times better. So you can see here, these are 2 images of the galaxy NGC 1309 in 2002 from the Lick Observatory in California, and 2005 from the Hubble Space Telescope Advanced Camera for Surveys, ACS. Now, they were studying a supernova, so you can see there's a supernova there that isn't there. But what you're concentrating on is the fact that suddenly it breaks out into spots and structure, and you can really see what's going on. It's completely transformed. Okay, and then here's another nice example. Astronomers have always wanted to systematically survey the sky, to map it out, to see what's out there. That wasn't there before. It's a supernova. It's by Piazzi Smythe himself, about 1860. And then, of course, over time, what people would do is to collect all those observations over many years, make them into great big tables, and then print them, bind them in books, and send them around to other scholars, observatories, universities, etc., so that everybody would have the information from your database. So that's how it was done, and that's the Edinburgh Star Place Catalogue from, well, it was started in the 1830s by Thomas Henderson and completed in the 1880s by Piazzi Smythe, and then finally published. So we were still doing this sort of thing up to the 1990s. Here in my office, this is the IRAS Point Source Catalogue. In fact, I've got one of the volumes here. You want to come look at it later on. Do you want to show people that, folks? If I go here, you can see here. Here it is, the IRAS Point Source Catalogue, and there are just pages and pages, and over many volumes, because the IRAS satellite detected hundreds of thousands, maybe millions, I can't remember the number, of infrared sources over the sky. So at the time, this was actually on computer, and it still is now, but in the 1990s it was still felt necessary that you had to make a kind of printed version as well. And these days we don't bother. Okay, and if you want to be even more sort of ancient, a little bit more modest, here's this is the Ariel 5 high latitude catalogue of X-ray sources by yours truly and others, and so that's a much smaller catalogue of a few hundred things, but X-ray sources in the 1980s were pretty rare. So anyway, that's you can come and see those later. Okay, back to the slides, I think. Yeah, great. Cool. Right. Then, in the late 19th century, people realized that the right way, the best way to systematically survey the sky was using the wonderful new technology of photography, okay, to take pictures of patches of sky, just go across the sky with, you know, loads of stars all in one go, and stack them up. So in 1887, representatives of a variety of observatories all over the world got together and decided to collaborate, to divide the sky up and all do some each, and cover the sky. And that project was known as the Carte de CL. The meeting was in Paris, and you know the French were pretty hot those days. So the Carte de CL was never finished. But there was a kind of precursor survey, which wasn't quite as deep, called the Astrographic Catalogue, and that was pretty much finished. And Edinburgh had a role to play in that, along with collaborating with colleagues in Australia, which is another continuing story. So here, this is the plate holder at the back of a telescope that's now in a museum in Perth, in Western Australia. They took the plates. Those plates were then shipped to Edinburgh, where I say we, I wasn't born, you know, the people of that time. I'm quite old, but not quite that old. So we measured the plates, you know, what was the positions of all the stars, the brightnesses, etc. And then they were shipped back to Perth, where they're still stored today. But we kept a few. So this one here, this is an astrographic catalogue plate that's still in storage in Edinburgh. So yeah, that's it. Not one of the things I've got to show you here, I'm afraid, because I think it's a bit too precious, that one. Right, so this game of both of photographing the sky and of collaborating with Australia kept going throughout the 20th century. Here is the UK Schmidt Telescope in Siding Springs. And this, I bet there's one or two people in the audience who know who that is. Go on, Alan. Sorry? That's Andy Longmore, yes. That's Andy Longmore doing something. So, that took glass plates like this. So this I like this picture because it involves both of your honorary presidents, because this picture was taken by me, but the hands holding this plate are those of Catherine Hamans. And you can come and see this in a little bit. But I do have that plate right here, and you can come and see what a real Schmidt plate looked like. So you can see they're physically quite big. Did you get that? And each one of those is 6 degrees by 6 degrees across. In other words, about 12 moons by 12 moons, roughly speaking. So this, that telescope, the UK Schmidt Telescope, and the Palomar Schmidt in California, between them, surveyed the whole sky, kind of starting in the late 1950s, going all the way through to the 1990s, when it was pretty much done. And the UK Schmidt plates, were all transferred to Edinburgh, where they were measured in a special way I'll come to in a second. So here's Alan's next test. So who's that? It's Sue Tritton. That's Sue Tritton. So this is the Schmidt plate library. And every time the southern sky was surveyed once in one waveband at one time, that was about 850 plates, and that was done several times. And then there were other plates. But altogether, there are thousands of these plates. And then there was a kind of industry from those days where we made film copies by sort of fancy contact printing, basically, and to make lots and lots of atlases, which were then sold to universities and observatories around the world, so that everybody had their own copy of the atlas of the sky. Okay, so that was how it was done in the 70s and 80s. Oh, that was me. I was just making a white screen in case I could hold up one of those plates, but it's too far away. I won't try that. Right. So then the big thing in the 1990s was digitizing the information on a plate like that. So this was done using SuperCosmos. This, just so we don't have to stress Alan too much, that's Harvey McGillivray. So SuperCosmos was basically like a giant scanner, okay, like you've got at home, only much more accurate. So all those plates were scanned to turn the information on them into digital information, put it onto big computers, where it still is now today. And there's a web interface, and anybody can go to the web page and to get little cutouts or search for objects. And so that's how a lot of science is done now with those online databases. But it started as those photographic plates which were then digitized. Now, of course, in more modern times, we're still surveying the sky, but the detectors are electronic, digital in the first place. So we don't have to start with photographic plates and then digitize them. It's electronic in the first place. So there's been a number of survey experiments, but the latest one that we're involved in is this. This is the Vera Rubin Observatory, which starting in next year, we hope will be conducting the Legacy Survey of Space and Time, LSST. Okay, and now it's nearly built. And I could have shown you a picture of the real thing, but I like showing this artist's impression because it's got this sort of stream of binary digits coming down from this. One way or another, you've got to make a physical change in some kind of material. It's about silver nitrate crystals being light sensitive, so they would darken in the presence of light. So you've made a physical change that records the light that fell on that photographic plate. Here's the inside of a modern camera, and there's the CCD. And in a CCD, the photons are basically knocking electrons out of one place, making them drift somewhere else where they get trapped in a sort of well. And then you collect them over time. And if you want to see what the inside of one, this have some kind of recording medium. It does several things for you. Firstly, you can integrate. You can keep adding up the light, okay? And so you can go deeper and deeper. You can see fainter and fainter things. So that's the big thing, number one. Number two, what you make is permanent. It's not a fleeting impression on your eye that you have to remember and tell somebody about later. It's a permanent record. Is that it's objective. Right? When you show people your photographic plate or your CCD picture, you're all looking at the same thing. Okay? The next thing is that it's measurable. Once it becomes digital information, then on your computer you can analyze the brightness of the different objects, measure their distance separations. Of course, you could also do it on photographic plates, and that's what, when the Perth astrographic catalogue plates were coming back to Edinburgh, that's what they were doing. They were looking at the little specks and going, what's the distance between that one and that one and that one and that one, right? You can make measurements, take your time and get it right. But finally, and this will be particularly important in the last section, you're not necessarily limited only to normal visual light that you can see with your eyes. You can detect and record other types of light. So for instance, in the bottom there, that's the U-Curt wide field camera, which is what was used to make that picture of the Milky Way that I showed you earlier that we blurred. So a big infrared camera that was used to survey the sky in the infrared, and we'll come back to the infrared in a little bit. Now, good old Piazzi Smythe again. He was a photographic pioneer, amongst other things. He was one of the first people to read Fox Talbot's papers and tried to duplicate his experiments. He was in South Africa at the time, together with John Herschel, who was also there. They made so-called calotypes. This is from 1837, I think, so it's one of the very earliest pictures ever taken, and I think almost certainly the first photograph taken in South Africa, and that's the observatory in South Africa, taken by Piazzi Smythe, and that's stored at the observatory as well. Oh, actually, no, that one is in the library in Glasgow. So Patsy Smythe, I'll stop going on about Piazzi Smythe in a bit. he was amazing. He was also a pioneer of stereo photography and of flash photography. So at the top there, that's a picture taken from that famous trip of 1856 on Tenerife of one of the telescopes he was using. And in the bottom there, that's Jessica standing next to a tomb inside the Great Pyramid of Giza on their Egyptian trip. Now, and they're stored in Edinburgh. That's Karen Moran's hand lifting out one of the stereo photographs from the box. And bottom right there is another thing too valuable to bring. It's the camera which Piazzi Smythe took to Egypt and made those flash photographs inside the Great Pyramid of Giza. And at the time, this was a very, very compact camera. Okay, it was small. Pioneers, and I think by that time Piazzi Smythe was off to other things. He was still working there, so he could have done it, but he didn't. Now, here's some more treats for you. So we can switch to the camera here, and you can see the live view of these. Some other things I brought with me that you can see. By the early 20th century, taking photographs with telescopes is extremely normal, and this, and certainly including from Edinburgh. So are we seeing this on sort of Zoom and YouTube okay? Right. So this is the solar spectrum taken in 1920 from Blackfoot Hill. This one for some people will be a real treat. This is the spectrum of Nova Herculis in 1935, very famous outburst. And this one here is the Orion Nebula taken with the Schmidt Telescope at Monte Porzio, which was in Italy, as you could tell from the name, and was a collaboration between Edinburgh and Italian astronomers. It was a kind of ROE outstation, and that's from 1971. And behind this at the back here, this is a film copy of one of those Schmidt plates we were talking about earlier. Oh. Do I need to say any of that again? So it's all right. So there we go. Solar 1920, Nova Herculis 1935, Monte Porzio, Orion Nebula 1971. Done. Right. Okay. Right, that's it. So let's move on. And there for the folks in the hall, there it is on there, and you can come and see it later. Right, and there's a white thing we're not using again. Now, so you could take great big bits of sky at a time with a Schmidt plate, but to get to that sort of depth that we're showing there, would take an exposure of about an hour. Okay. Now, by the time digital detectors came along, like those CCD cameras, and such as every amateur's got these days, etc., and we've all got in our phones, you could get a picture like that in a few minutes. Okay? They're much faster. And this is about quantum efficiency. Of the photons falling on a photographic plate, only about 1% actually have that effect of doing the darkening thing that you want. Right? Whereas with a CCD camera, the kicking out electrons and trapping them, typically 60 or 70% of photons do that. Okay, so they're much faster. However, photographic plates were still groovy for a long time. So here I'm sort of comparing the size of one of those CCD chips with the glass plate. So they were tiny. So to map out that kind of area that you get in one go on the plate, you'd have to go... Yeah, so it just took a long time. And so that wiped out the speed advantage that it had. So the surveying of the sky was still on the big photographic plates for quite a long time. So that changed in the 2000s when we figured out how to mosaic CCD chips. So this is the CCD mosaic that's on this telescope here, Pan-STARRS, which was led by people in Hawaii, but again, it involved some of us in Edinburgh. And you could see it standing next to John Tonry there, or John Tonry standing next to it. So that was as big as a Schmidt plate, but it was a CCD. So now you could do surveys really, really fast, and we've never looked back. All right, so that's the end of surveying the sky. Final section. There we go. The multi-wavelength sky. So light is an electromagnetic wave, but our eyes are only sensitive to a small fraction of the wavelengths that are potentially present, as I'm sure you all know. But there's much more to life than visible light. There's infrared, there's radio waves, there's UV, there's X-rays, there's gamma rays, and all those are now studied by astronomers. And objects in the universe emit waves of all those kinds to teach us lessons about the universe. So that's been the big explosion in astronomy from the 1970s onwards, and keeps on accelerating. Now, in Edinburgh, after a brief foray into UV astronomy in the 70s, the big Edinburgh thing has been long wavelengths, but not as long as radio. Infrared light and sub-millimeter light. So sub-millimeter light's like very long wavelength handheld infrared camera. And you can see, her head's much hotter than her clothes here. The windy, and I have it here for you to come and see. So the very first IR cam, infrared camera, was on the telescopes in the mid-1980s. And I'm very pleased to tell you that the man that wrote the software for that camera is sitting right there, Ian Smith. So he's a hero of this story, and was up on the telescope with IR cam. So this isn't quite the first one. This was the third generation IR cam 3, but only a few years later. It had a massive chip, 58 by 62 pixels. This is what an infrared camera looks like now. Okay, and I'll show you. It's great, this. I can clip this onto my iPhone. All right. Right, and there you all are. Right, that's you lot. Okay, and this cost several million quid to build. I bought this for 200. Okay, I coupling one of these to a telescope would be an interesting challenge. I've been meaning to kind of think about that for a while. But anyway, you can all come and play with this later as well. But yeah, mid-80s, mid-20s. So that's how technology has improved. Right. I'll just shut that off for the moment. So there's still, historically you would do this with one sort of pixel at a time. Basically, like a radio telescope, you'd have an antenna and detect a signal, and then you'd have to move it somewhere else. So this was the revolutionary thing built by the ROE in the 1990s. This is SCUBA, the sub-millimeter common user bolometer array. Okay, and basically it's a kind of little array of feed horns, and at the bottom of each one of those feed horns is a bolometer. Okay, so it could build up a sort of crude picture, and that lived inside here. And then SCUBA 2, which I don't have a picture of, I'm afraid, but then that used these boxes here. They're not big because the detectors were big. So this thing was about this big. Right? They're big because helium to keep them really, really cold, so that they can be as sensitive as possible. And to show you the sort of thing you can get, so there we are again with the optical view of Orion and the infrared view of Orion. Now, I'm cheating here a bit in two ways. The sub-millimeter view, this isn't actually what you would get from something like SCUBA. It's some proper radio telescopes measuring carbon monoxide molecules. But I say somebody else made this picture. It's superimposed on a kind of suburban scene just to give you the idea. Okay, so the Orion Nebula is just inside here, and you can see now that the Orion Nebula is just one part of a huge complex of cold molecular gas that is the raw material for making new stars. So that's what you're seeing there. And if it wasn't for sub-millimeter astronomy, you would have no idea this even existed. All right, so the latest, we're getting close to the end now, possibly the most exciting bit. The latest episode in this great Edinburgh adventure of the infrared is, of course, the James Webb Space Telescope, JWST, or as your other Honorary President likes to call it these days, the Just Wonderful Space Telescope. And so just a few. So this is the Cliffs of Carina. So that's not a mirror image, that's an NIR cam image, but it's very, very beautiful. This is Stefans Quintet, 5 closely packed galaxies, and this is a sort of a composite of near cam and mirror images put together. Possibly, has anybody here observed Stefans Quintet? Have you tried going for that? Mark says yes. Yeah, it's pretty groovy. So I was showing my age there, groovy. But it is. Little Simon and Garfunkel moment coming on. This is a cluster of galaxies called Smax 0723. And it's not that far away. But you see, there's lots of little streaks here. Those streaks are galaxies which are much further away than the cluster galaxies, are way behind it, but their light has been magnified by gravitational lensing by the mass of the cluster. Okay, so they appear much brighter than they should do for the things at that distance, which is very, very groovy, because you can then study things further away than you would have been able to otherwise by using that cluster as a kind of giant telescope. So that's something there. Now, what about this edge of the universe thing? In a picture like this from JWST, there's kind of little faint dots all over the place. They're at a variety of distances. Some of them are relatively close, some of them are way far away. How do you find the ones which are out there at the greatest distances that we're so interested in these days in cosmology? Well, here's how. Basically, you look for very red things. So you see this picture up here. It's a tiny little piece of a JWST image. And you can see two things here. You see there's a kind of fuzzy blob, which is bluish, another bluish thing here, and then, but in the center, okay, and so that's a kind of all the pictures, but it's kind of fading out by the time you get to the red end. Now, on the other hand, this spot here, it's quite bright here in the red. There it is, there it is, there it is, and then suddenly it's gone. In the bluest filters, it's just not there. Now, that sort of cutoff is something you expect in the ultraviolet of starlight, of galaxies. So the fact that happens in the infrared is exactly what you expect. So this is the most technical part of the talk to finish with, but exactly what you expect with the expanding universe. So the light is stretched to the red, and so there's nothing left in the bluest filters, and it's all way in the red. And from that, you can try and estimate the distance of that object. And this is at a redshift of 12.63. And I think it's probably the most reliable very high redshift. There's been a few come and gone, right? But that's been confirmed in various ways. Okay, so now we've got to the edge of the universe. I think that's where we probably better stop. And I'm just going to finish off with this picture, which is just one of my favorite pictures ever. Now, this is not an Edinburgh picture, but it's just so beautiful. And this is the Helix Nebula as imaged by the Spitzer Space Telescope, which is in some ways the kind of predecessor of JWST. So it's just awe-inspiringly beautiful, and I think a good place to stop. So that's everything I got for you. Thank you.
Thank you, Andy. That was fascinating. We do have a little time for some questions. We've got quite a full evening, so I'll just maybe a couple of questions if anyone's got.
You can ask lots when you come up and look at stuff.
You can come and see
later.
afterwards as well if you're in the hall. Has anyone got any questions just now? Or if you're on Zoom, we've put it into chat. No?
Crikey. I've never known this lot so subdued.
Hello, Radham. Can you hear us?
Yes, hello. Thank you for the great talk, Professor. And we don't have any questions.
No questions, right.
So it must have been the greatest presentation of all time.
That's great. Thank you very
Fascinating.
much again. Thank you. Oh, we've got one over there.
Thank you, Sean.
I'm not going to let our Honorary President get off the stage without asking a question. Sean Wexted, hello, here in the corner. It was actually just about the James Webb Space Telescope. You were saying what Catherine was calling it. Is it living up to your expectations of what you expected it to deliver in terms of a quantum leap above what we already had, or is it actually redefining what you thought it would do? Because, I mean, it's only been operational for, what, about a year?
About a year.
About a year-ish. And then there was testing phase as well.
I'll give you,
just in terms of how is it changing the profession?
I'll give you quite a nuanced answer to that question. So in terms of the sheer data quality, it is amazing. It's every bit as good as we hoped, in some ways better. It was, as you know, delayed a lot, and so some people were quite skeptical, but it turned out to be absolutely perfect. Everything works amazingly well. The data quality is incredible. Now, in terms of science, it's and its impact, it's all definitely already very good. There's some groundbreaking things, mostly about high redshift. Now, just it's a question of how big the superlative is, whether the things that JWST is doing are simply very, very good or absolutely kind of transformative. I think that will take another few years to know. Okay, but it's certainly absolutely not a disappointment and is pretty amazing.
Thanks.
Well, thank you again for that amazing talk. Really enjoyed that. Thank you. Okay, we're going to move on to the sky in June, if I can get my laptop to respond. Thank you. The pointer's not working, so let's just keep on. We've got Jim Nisbet doing that for us.
Thank you, Mark. Excellent. It doesn't seem like 4 months since the last time I did this. The occasion does seem to have come round rather quickly. Hats off to Alan and Horst, who would be doing this every other month, all the work they put in to do that. Once again, I'll stress I'm not really a card-carrying observer, so it won't be a full-on detailed guide. I'm sure everyone can't wait until we get to the SGM and AGM anyway, so I'll try and not keep you from that excitement. So as always, the sort of go-to source is Alan's Scotsman column, which is also published on the ASE website. I'll start with the times for this month. Turning back to the last time I did this, there was about 9 hours of daylight in February, and it's now 17, quite a difference. So we have the longest period of daylight coming up, and no dark sky at all, effectively. Compare this with February, when there was about 10 hours of darkness. So in that case, I think I'll just stop here and say, well, there's nothing to see. Not quite. You're not going to get away with that. So it's not quite that bad. Of course, June is the month of the summer solstice, and we have a sort of bit about the sun here. So the actual time of the summer solstice, I had down in 1557, although I see Alan's column said it was 1558. So I will bow to his expert detail rather than mine. There's a very timely article by Ramsay McIver on the ASE website, which tells us about the phenomenon and the clouds, which are a very high altitude, 80 kilometers, much, much higher than the normal clouds, formed when microscopic dust particles and ice crystals combine to reflect sunlight. It does seem to be a bit hit and miss to try and forecast when people might see these. So it really has to be a case of going out and looking up into the sky to see an hour after sunset to an hour before sunrise. I don't have a great image of the moon this time to illustrate my slide, but I thought speaker's prerogative. I put an image I took on this week, just sticking my SLR camera out and grabbing this shot just as the sun was going down. Full moon is going to be on Sunday, and the full moon in June is sometimes known as the strawberry moon in the United States because of picking wild strawberries, or the rose moon in Europe. There seems to be a bit of a difference as to whether rose is about the colour or whether roses are in bloom. Nobody seems to be very definitive about that. It is a good time to remind people that the moon is the first item in the ASE 24 observers list, with 4 different features to look for. I'll quickly just skip on to the table of the planets. I'll not go through everything in detail here. The best ones that we'll have a chance to see this month are Venus and Mars. Mercury is very difficult because it's rising only just before the sun. And Jupiter and Saturn, although morning objects, are either low or just rising. So it's going to be sort of not very easy. And then Uranus and Neptune, of course, really from Edinburgh is going to be binoculars for Uranus or telescope for Neptune. So speaking of Mars and Venus, looking to the northwest, this is timed for a little bit later on this evening, just into the next day. They are quite low towards the horizon, so it is going to be a bit tricky to get dark enough and to see them. Looking from Venus to the right on the image, going through the star Capella to the W of Cassiopeia, which is one of the most recognizable constellations in the sky, and also having 5 stars which are all reasonably of similar brightness makes it easy sort of objects for the naked eye to spot. And Andrew Farrow, looking towards the southwest, there is Spica in Virgo and Arcturus in Boötes. Let me just go on to the west. I was tempted to say that actually there isn't much of interest to see in the west at this time of year, but I've mentioned Ursa Major because a couple of the observers in the Flickr group have posted some images from the area nearby the magnitude 1.8 star Alkaid at the end of the Bear's Tail in Ursa Major. So as reported in Alan's column, this is the location near where there's a recently discovered supernova. And Pat Devine posted this image of the Pinwheel Galaxy M101 with the supernova location marked. And then just below Alkaid, you can find M51, which was imaged by Bill Bonner, also from the Flickr group. So even although the skies may be too light for those of us with just eyes and maybe a pair of binoculars, the ASE members just are keeping on doing their deep sky work and producing these images. At which point I will stop and we can get on to the SGM and AGM.
It's fine to see it now. Thank you, Jim.